Okay.
Okay. Yeah, we can begin. It's a great pleasure to introduce Satya Reddy, and he'll be talking on a gateway to the circle method, Ramanujan sums and the ternary Goldbach problem.
Yeah.
Go ahead, Satya.
Yeah, thank you, Gaurav. I'm thankful to your team and you for inviting me and also giving this opportunity to share some applications of Ramanujan's with all of you. Okay, so this is actually I work in Ramanujan sums. Basically, when I work in my own problems like graph theory, these sums automatically came. Okay, now I'm want to see that actually where actually they started, Ramanujan started. So I came to know that in the beginning of these Raman sums are circle method related to circle method. But I'm not a good expert in the additive number theory side. But I will try to see that where these Raman sum come. That's why I wrote gateway to circle method. So it will go like this. Introduction to Raman sums first, then gateway to circle method. Some applications of Raman sums. Here where I used Raman sums, I want to explain you. If time permits, I will explain them. Otherwise, I will just go through them. Okay. So more than a century ago, Hardy and Ramanujan wrote a landmark paper on partition function. Right. The paper title is that asymptotic formula in combinatorial analysis. It is published in Proceeding of London Mathematical Society. So there is a website here, ramanujansrinidhi.org. There also they uploaded old papers and some other things. Those interested can see there. Okay, this paper was significant for two reasons. On one hand, it was the first paper to have determined the asymptotic behavior of the partition function. On the other side, it was the significant in that it introduced the circle method to number theory, which later became an effective tool to study additive questions. So you all know that partition function has a series like this, expansion like this, Euler formula. It is provided by Euler. It is one side we have a series, other side is a product of product terms. It's called Euler product formula for the partition function, where P of n denotes the number of partitions of n. That is P of 0 plus P1 of x plus P2 x square and so on is equal to 1 by 1 minus x into 1 minus x square and so on. You know that 1 by 1 minus x means 1 plus x square and so on. 1 by 1 minus x square means 1 plus x square plus x power 4 and so on. If you multiply, you can easily see that the coefficients of x power 5 will give number of partitions of 5, right? It is easy to see this thing. But the interesting thing to observe here is that here you see that one side we have this 1 by 1 minus x, 1 by 1 minus x square and so on. In particular 1 minus x, 1 minus x square and so on. So this series not defined at the nth roots of unity. So nth roots of unity are playing a role, right? So that is interesting point here. That's why in the circle method also we are going to consider unit circle, right? And mostly we are talking about the nth roots of unity. Okay. So what is a Raman sum first, right? So n is a complex number z is called an nth root of unity if it satisfies the equation x power n equal to 1. That is, it satisfies meaning z power n equal to 1, right? A primitive nth root of unity meaning that it is nth root of unity, but it is that means it's z power n equal to 1. It cannot be z power k cannot be 1 if k is less than n, right? That means it is not 1 before between 1 and n minus 1. It is 1 only at n, right? They are called primitive nth roots of unity. So all nth roots of unity, out of which few of them are primitive nth roots of unity. So for example, we'll denote this notation zeta n equal to e power 2 pi I by n. It is a primitive nth root of unity. So all nth roots of unity are distinct. Why they are distinct? It is easy to see. They are the roots of the polynomial x power n minus 1 equal to 0 or equation. So if you look at x power n minus 1 derivative, that is n into x power n minus 1, their GCD is 1. So all the roots are distinct. That is easy to verify. And geometrically, these are points on the unit circle with one vertex at 1, 0, right? Yeah. So if I am going little faster, please let me know. Or anything you are not clear, please stop me. I will explain it that instantly. So algebraically, they form a group. That is a beauty. So the roots of a polynomial forming a group. In fact, it is a cyclic group. These primitive roots are exactly the generators of that cyclic group, right? So that means zeta n power k is a primitive if and only if k comma n GCD is 1. Okay. So obviously the number of primitive roots of unity is equal to the Euler-Torsion function phi of n. Okay. So the number of primitive nth roots of unity is exactly phi of n. Okay. So an example, if you take sixth roots of unity, so I told you zeta n is e power 2 pi I. 2 pi zeta n power k means e power 2 pi k by n, right? Now, if I take n equal to 6, then these red vertices, that is e power 2 pi 1 by 6 and e power 2 pi 5 by 6, 1 comma 1 comma 6 GCD1, 5 comma 6 GCD1, these are primitive, but remaining are not primitive, right? But they're all nth roots of six roots of unity. Okay, so there are some few simple results on nth roots of unity. If you add all of them, it is going to be 0. Okay, that is easy to see if you take the summation. So it is a geometric series, so we can geometric sum, so we can easily get this. The other way is also that sum of the roots is the coefficient of x power n minus 1. The roots of this polynomial x power n minus 1. So automatically sum of the roots is here 0, right? Another way to prove this. Okay, and it is in fact k is not equal to 0 mod n, even then also zeta n power k equal to 0. These are going to be useful for us later. What happens if n divides k? If n divides k, then it is like zeta n power 0. We're going to get n, right? Hope it is clear. Yeah. So when k is not equal to 0, still the sum is equal to 0, right? Okay. And further, we can see that x power n minus 1 is equal to product of d divides and phi d of x. These are phi m of x is the mth cyclotomic polynomial, right? Yeah. Any questions, please? Okay. Right. So these phi m of x is a mth cyclotomic polynomial, right? Yeah. Okay. And that means that actually their roots are primitive mth roots. Okay. So all the roots are divided into primitive mth roots for each divisor d. So I will explain that in a while. But interesting feature is that the degree of this cyclotomic polynomial, mth cyclotomic polynomial is phi of m. So we have a beautiful expression that Gauss theorem will come here. N is equal to summation d divides and phi of d also can be derived directly from here. Okay. So Ramanujan published a famous paper that on certain trigonometrical sums and their applications in the theory of numbers. That is, so in this he proved several nice properties of certain finite sums, which are now called Ramanujan sums. Even though Dirichlet and Dedekind already considered these sums in long before, but according to Hardy, Ramanujan is the first to appreciate importance of these sums, use them systematically. Ramanujan play a key role in the proof of famous result due to Vinogradov asserting that every large odd number can be written as sum of three primes. This is called ternary Goldbach conjecture. I will explain in a while later. These sums have numerous other applications in combinatorics, graph theory, even in physics, several places. In particular, I work in a graph theory. There is some area called circulant graphs. Circulant graphs means whose adjacency matrix is a circulant matrix. Matrix is circulant matrix. First row we cyclically shift. Then obviously it is a polynomial in full cycle permutation matrix, right? Then its roots are nth roots of polynomials in nth roots of unity. All circulant matrices roots are actually polynomials in nth roots of unity. So that means in particular, um, so you take 0, 1, 0, 0 first row, 0, 0, 1, 0, 0 second row like that. If you take that matrix, that is called full cycle related to permutation. 1 goes to 2, 2 goes to 3, and so on. N minus 1 goes to n and n goes to 1. unka permutation matrix if you take, then so whose minimal polynomial or characteristic polynomial is x power n minus 1, right? So a circular matrix is a polynomial in that. That's why roots are that one. So this that I used it several times in my works. Okay. Now we are formally defining what is Ramanujan sum. It is exactly that Cn of k denoted as Cn of k. It is uh, e power 2 pi I by n power k ka sum. That is a sum of kth powers of the primitive nth roots of unity. Okay. So for example, if I take zeta n is equal to e power 2 pi I by n, I'm recalling one more time. It is you are taking their kth powers. Okay, where j comma n gcd1. When j comma n gcd1, zeta n power j become primitive nth root of unity, right? I'm taking kth powers of the primitive and their sum. That is called a Ramanujan sum. Okay. In other words, simply sum of the kth powers of primitive nth roots of unity. Okay. So for example, to understand, I'll give some more notation. If you take Rn as set of all nth roots of unity, 1 zeta n and so on, okay, it here all nth roots of unity. These are the roots of the polynomial x power n minus 1. But whereas if you take mn, okay, these are set of primitive nth roots of unity, where GCD of j comma n 1. We can write Rn equal to union of these, okay, union of d divides n md, where md is set of all primitive dth roots of unity. Okay, then Cn of k is simply summation of x power k, where x belongs to mn, right? Yeah. Hope these are clear. Please stop me. One more example to make it clear. If you take R4, what is R4? Fourth roots of unity. That is 1 minus 1, I minus I, right? Then M4 is I minus I. Okay. R4 is singleton 1 minus 1, I minus I. Why I separated like this? 1 is a primitive 1th root of unity, minus 1 is a primitive 2th root of unity. I and minus I are primitive 4th roots of unity. Means I power 4 is 1, but before that it is not 1. Okay, 1 minus 1, I minus I, all power 4 if you do, I'll get 1. But I and minus I will get only at 4. That's why they are primitive 4th roots. Okay, now what is C4 of 1? That is I power 1 plus minus I power 1. Okay, that is 0. What is C4 of 2? I square plus minus I whole square. That is minus 2, right? C4 of 3 means I cube plus minus I whole cube, like that. So easily you can compute, and it is a periodic. So 0, minus 2, 0, 2, they will come. And the interesting thing is that if you take a cycle graph with 4 vertices, the eigenvalues are going to be this. That is a circular matrix. That's what I'm telling earlier. So in my works, the Ramanujan came very frequently. The first remarkable property of Ramanujan is that they are integers. You can see that all of them are integers. So Raman showed that several arithmetic functions, that is functions defined from set of positive integers to be, so have these Ramanujan expansion. So I will tell you an arithmetic function f has a Ramanujan expansion if f of k is equal to an cn of k. So we are expanding in terms of Ramanujan sums. Okay, where an is a coefficient. Okay, there are many like that. So for example, if you take number of divisors function, tau of m is the number of positive divisors of m. Then tau of k is expressed like this. It has a Ramanujan expansion, Ramanujan series expansion. Euler phi function has a Ramanujan series expansion. Means we'll get Ramanujan coefficients, right here. Yeah, and Mangold and function are many things. In fact, sorry, 1 minute, something happening. Okay, yeah, okay. So in fact, so Ramanujan further discovered that prime number theorem is also equivalent to in terms of the Ramanujan sums. Okay, yeah. So there is a Klosterman sum also. That is also that is actually came from Ramanujan sum. Yeah. Okay. So now we are going to prove that result. Ramanujan sums are integers. In fact, we'll prove better result. Cn of k, okay, Ramanujan sum is equal to summation d divides gcd of k comma n d times mu of n by d, where mu is a Mobius function, right? So we also have that n is equal to d divides n phi of d. By Mobius inversion formula, we have this. Look at these two boxes. Okay, you can see the similarity. D into mu of n by d, that is common. You see the beauty. Only thing is that here d divides n, whereas there it is. So am I audible?
Mm,
Yeah.
There is a like we are not able to see your screen now. Something. Yeah, now we can see it. Yeah.
Okay. Yeah. So you can see that these two boxes, black boxes, so they are very much similar, right? So here D divides GCD of K comma n, here D divides n, right? Just observe that one. I just put it here. So this shows that so we are not yet proved this theorem, but if you prove it, then clearly Cn of K is an integer, right? One can easily see that. And Cp of K, that is primitive pth roots of unity, right? So you know that cyclotomic polynomial for P is prime number is that 1 plus x square up to x power P minus 1. So sum of the its roots is minus 1, right? If P divides K, then it is exactly P minus 1, right? Similarly, for P power M, we can easily see these things. So in particular, by this is actually a multiplicative property. We can show that Cn of K is equal to, finally, we can prove this way. But now I'm going to give the proof of this theorem, but that is also very simple. If you call eta n of k as sum of all nth roots of unity, right, that we can write it as summation d divides n. You know that all nth roots of unity can be written as union of primitive nth roots of unity, right? Because of that, I can write this sum primitive plus adding like that. That is exactly CD of k, primitive sum, right? So, but we know that individually, we know that sum of all nth roots of unity is 0 if n does not divide k and if n divides k. That we proved earlier. So by using this, we have this result. Okay. By again Mobius inversion formula, right? So while studying the roots of the polynomials also, you come across these things. This is another proof. I will skip little, I'll go little faster. You know that if you take any polynomial, so we can write like this, then we know elementary symmetric polynomials and all. So from that also, it is a beauty that we will get these things, Newton polynomials, and from that also we can derive the properties of the Ramanujan sums. Okay, so I'll just skip this, but very interesting to get from there also. Somebody is interested, they can pause the video and observe them, right? So I request that whenever you have a non-clarity, then please pause the video and go through carefully and proceed. Okay, please follow this, pause, review, and proceed. Pause it, so little bit review and then proceed. Okay. So phi n of x, you know Euler, this phi n of x, cyclotomic polynomial, their roots are exactly primitive nth roots of unity. So from that also we can derive that sum of nth roots of Cn of k value is equal to mu of n when k equal to 1, right? Yeah, okay. So in particular, what I want to say that can be derived from here also. If you take a k is equal to 1, right? If you here in this formula, if you take k is equal to 1, I'll get, so d becomes 1, mu of n will get, right? Only one sum will get. So just the sum of the primitive nth roots of unity is mu of n. That's what I want to convey. That we will use later. Okay, right. So now this is about Raman sums. I'm not shown where I used them, or I used meaning when I working, they came naturally. That I will show at the end if time permits. But my goal from now onwards is that actually where they started. Okay, of course, before that, as I mentioned, Davenport and other people, they got little early also, but majorly they come up, appreciation becomes from the Ramanujan. Okay, so now the next from here onwards, part two. I'm going to take up. I collected my content from the following videos. One is Stephen Joel Miller, and Kaninika Sinha from ISER Pune. Her video, so it is actually available. Ganita Sora they conducted it, and I watched that video also. To some content collected from there also, not me most of it, and also there is a one video, the obviously true theorem, but no one can prove. One other video is available. Okay. And there is a nice harness project. This also I noticed. So I request that to please pause and then go through them. So there is a book, Introduction to Circle Method by Ramurthy and Kananika Sinha. And also I watched one Surya Ramana sir video. It is an IMSC Chennai channel. So there also you can watch. So content is collected from these places. Okay. So it is better that you also, whenever time permits, please watch these. So a natural number n greater than 1 can be written as product of primes. We know this, right? So it is no need to mention finite. N is finite, so product of primes also finite. Finite number of products only. So this is well known. It's called fundamental theorem of arithmetic. There exists an m so that every number can be written as product of at most m primes, right? But for answer is clearly no. We all know, because if I take a product first m plus 1 primes, right? If I take my number n equal to p1 into p2 into pm plus 1, where p1 is the first prime, 2 p2 is second prime, 3 and so on, then I cannot express n as product of m primes or less, right? So that answer is no for that. So with finite number of primes are not sufficient to express every number, right? But what about additive way? That is, if you take a number n, can it be written as sum of primes? First of all, yes, the answer is yes. We can simply write even with 2 and 3. Every natural number can be written with just 2 and 3. For example, if we take 25, right? So 3 some 7 times, 21 plus 2 plus 2, right? If in particular, what we are saying that if you have unlimited supply of 2 rupee coins and 3 rupee coins, if I go to market, I can purchase anything. It is called coin exchange problem, right? So we can purchase anything item greater than 1 with the 2 and 3, because I am purchasing 2, 3, then again add 2 to that, right? Only with the 2 itself I can purchase everything, right? 2 and 3, 1 3 rupee coin sufficient. Okay, good. Is there exist an m such that every n can be written as sum of at most m primes? Here, this is increasing. Only 2 and 3 I will use. I cannot. That is also blows. But if I use all primes, the question is that is there exist an m such that every number can be written at most m primes? Answer is yes. Okay. So the goal of this talk is to introduce this concept and how Ramansam play an important role in this direction. Right? Okay. So actually, Shillman 1930 proved that so every number greater than 1 can be written at most d primes. So he used some sort of density thing. So I will not go into details of that. But recent bouncer, Ramare in 1995 proved that every even number can be sum of at most 6 primes. Torrenstow proved that every odd number greater than 1 can be the sum of at most 5 primes. Okay. This is a generalized to Ramare's theorem. Why? So by using this, we can prove Ramare's theorem also, right? Because if I take any even number, so even number I can subtract 3 from it, then it become odd. So that is written as 5 primes and 6 primes will come, right? Yeah. So this is the timeline for a ternary Goldbach conjecture. So for example, 1920s, Hardy and Littlewood, they proved ternary conjecture for sufficiently large and greater than C by using generalized Riemann hypothesis. Vinogradov proved that without any GRH, with unconditionally proved. But the problem here is that for a large C, they do not give the C. Hardy Littlewood or Vinogradov does not give that. They told that there is a large C. Afterwards, every odd number can be written as at most 3 primes. Okay, but that bound is decreased 1956 by so Borzakin and Chen and Wang decreased a very high way. In 2013, Herland have got actually improved completely. Means he showed that any odd number greater than 10 power greater than or equal to 10 power 27, so can be written as sum of at most 3 primes. Now by using computers, we can show that up to 10 power 27, we can use computers to show that there is sum of at most 3 primes. So by using these two, now it is clear that uh, so every number can be written. Every odd number greater than or equal to 5 can be written as sum of at most 3 primes. Yeah, sorry, one more thing I want to add here is that now it is clear that um, um, so every number is sum of at most 4 primes can be derived from this, right? Are you, I hope everyone able to see. Because every odd number we can write at most 3 primes. Now every even number also, now even number I'll subtract -3 from that I can show, right? So we done that. Now I'll go to more general setup now. If A and B are any two subsets of natural numbers, we define A directs from B, some set. It is x plus y, such that x belongs to A union 0 also allowed, B union 0, right? In particular, usually we'll define with two sets, but finally we'll confine to one set, right? When you define relations also, relation from A to B, finally relation on A, right? We'll take a single set and see relations on A. Like that, what is P plus P? Primes. Okay. So if you M fold some set, that is A plus A M times intersection with N. So the typical question is that there exists an M belongs to A such that MA equal to N. Okay. I take A is a subset of natural numbers and I add it to itself. Can I get entire N? Okay. After adding some M times, right? So this is the question. So basically, so we are looking for a subset S of N. We are asking these two questions: additive sufficiency. That means that every natural number can be considered as sum of elements from S, and boundedness at most also, right? So for example, you take squares, perfect squares, then Lagrange proved that every natural number greater than one, greater than or equal can be expressed sum of at most 4 primes, right? Okay, so what is the set S contains 1, 4, 9, like that, right? But every natural number can be written as sum of at most 4 primes, sorry, 4 squares. So this is generalization. Waring theorem in 1970 is, so he asked that every natural number can be written as sum of at most 4 squares, 9 cubes, 19 fourth powers, and so on, right? Yeah. Okay, so in similar time, Goldbach conjectured these two. 1742, he wrote a letter to Euler. It is believed that he wrote around 190 papers in their collaboration of 35 years. It is one of the paper, one of the letter. So every even number greater than 2 can be expressed as a sum of 2 primes. It's called famously binary Goldbach conjecture or strong Goldbach conjecture. Goldbach ternary conjecture is that every odd number greater than 5 can be written as sum of 3 primes. Okay. So once we prove that a strong conjecture, weak conjecture follows easily because we are discussing already. If n greater than 5 is an odd number, odd integer, so we can take k is equal to n minus 3. Then k is even and it can be written as sum of 2 primes. Then n can be written as sum of 3 primes by adding 3 to it, right? But the other side is not true. Means if you prove weak conjecture, we cannot prove binary conjecture. Yeah. Are there any questions till now? Is it okay? So can I proceed?
Yes, yes. Yeah.
Thank you. Yeah.
Mm.
Okay, so the setup is like this. Consider set A of non-negative integers, right? And so the question is that we define RSA of n. That is, S is some integer. RSA of n is that. So is it possible to write n as sum of S elements from A? That is A1 plus A2 plus AS equal to n, where A1, A2, AS belongs to A. So the RSA of A is the number of ways of writing that. Okay. So it is actually an integer, first of all, right? It is an integer. So note that, for example, if you take all natural numbers, so it is a partition, right? So 5 can be written as not partition function, sorry. In the partition, order is not important. It is just a compositions. So 5 can be written as 2 plus 3 as well as 3 plus 2. So these are also counted as a separately, okay? Right. So we are interested in estimating RSA of n for a specific values of S and sets A. It is a general setup, that original one, but we will work for special values of specific values of S and specific sets A. right? In particular, prime numbers if you take, and s equal to 2 is the binary conjecture, s equal to 3 is the ternary conjecture, right? Goldbach ternary conjecture. It's not conjecture now, it is proved. Okay, so that is the thing. Okay, in order to motivate the overall idea, so we'll consider something, right? So we take f of z in complex analysis. Z is a complex variable. So we take z power a. Okay. So if n, so yeah, we'll consider this, right? So f of z whole square becomes the summation square. So it is equal to like this, right? Okay. Yeah. So A of H into A of K. So C of N is this convolution product. You know that how do you multiply series or polynomials, right? It's a convolution product. You all know, aware of it. So that Cn is that product. So we can like that we can do power s also. So in general, f of z power s, it is equal to this. Then here we'll get this coefficient, right? This coefficient is the number of ways of expressing n as a sum of s elements from the set A, right? Yeah. Okay. Beauty. That is a thing. Okay. So the f of z power s is actually the generating function for RSA of n. Okay. Right. So how people proved it? So by using Cauchy's theorem, right? So we to find the coefficient, so we'll consider this integral 1 by 2 pi integration along the closed circle CP, C rho, right, with radius rho. Then we can substitute and see that we are going to get RSA of n only, right? So this is well-known Cauchy's integral. Okay, this is a precursor for because Cauchy is much older than these people, so he introduced these things in around 1850. Okay, so these are used. So Hardy and Littlewood and Ramanujan, so they used this and come up with this circle method. Okay, yeah. So this is the background. Okay, the origins of circle method. Circle method is powerful technique used to solve various problems in additive number theory by translating them into integrals of exponential sums. In 1918 paper that I told earlier, so they consider the root of circle method. Their work derived asymptotic formula for partition function, right? So later Rademacher famously studied P of n. So Rademacher, what he done is that there is a small problem in the Hardy Ramanujan. So they get some series S of m comma n that is an approximation to P of n, but that is diverges when m goes to infinity. But Rademacher little modified that. He modified a little bit and he got a convergent series. Okay, but I'm not going into details. Yeah, one can, if somebody is interested, they can see that Surya Ramana's video. Yeah, okay, that we'll get more clarity on that. Okay. So historical records show that in earlier letters to Hardy, Ramanujan already conceived the essential form of circle method before their formal collaboration. Circle method is in Ramanujan's mind for a long time. That is what important thing, right? Okay. So now we'll come to the actual thing, fundamental integral equality, right? So E of x we are defining as e power 2 pi x, okay? Cos 2 pi x plus I sin 2 pi x. So we know that it is periodic with period 1, right? Easy to see. Okay. So origin of circle method related to this. Okay, this is important one, identity integral 0 to 1 e power mx dx equal to 1 if m equal to 0, 0 if m not equal to 0. Why? If m is not equal to 0, points on the unit circle gets cancelled each other and we'll get 0. Hope easy to see. Is anyone has any questions here? Okay, I'll proceed then. Okay, if n is an even natural number, okay, in general, we can define for any natural number, but even natural number, because we are looking for Goldbach conjecture, binary Goldbach conjecture. For that, the setup, but otherwise, we can take for any. So f of x equal to e power px, e of px. That means e power 2 pi I px, right? Okay, so where p is less than or equal to 10, we are collecting all primes. For example, uh, if you take n equal to 10, right? If n is equal to 10, then e power e e2 of x, e of 3x plus e of 5x plus e of 7x will come, right? Like that. Okay. So f square of x is, if you multiply it, well, then exponential, so they become some p1 plus p2, right? Then you multiply by e power minus nx and integrate from 0 to 1. So we'll get exactly that number of ways of writing n as sum of two primes. It's a beauty, right? So our answer comes as an integral. Okay. In particular, z I replaced with e power 2 pi. 2 pi is. Okay, good, nice. So can we prove that the integral is greater than 0 for all n, sufficiently large even n in particular, right? So just I'll summarize what we done till now. F of x is an exponential sum over primes up to n, right? F of x equal to defined like this, right? Means n is fixed, okay? N is fixed. F of x is defined like this. Okay, then ternary binary Goldbach conjecture is same as proving this integral 0 to 1 f square of x e power minus nx dx is greater than 0. So we converted the problem into integral. So a number is written as sum of two primes is same as showing that this integral is positive, right? The ternary Goldbach conjecture is that f cube of x into e power minus nx dx. Okay, this integral has to be greater than 0, right? So more generally, so any d, right? Yeah. So this is the setup now. So beautiful setup that solving combinatorial problems by using integrals. Hope it is clear to everyone. Okay. So in particular, Vinagradev's identity we can say like this, right? Yeah. So in fact, he proved it. He proved for sufficiently large odd integers. Now entire theorem we can specify like this. Okay. So Halfgold's theorem also we can say like that. If n greater than odd for all integers n greater than or equal to 10 power 27, we have this. Okay. So proof of ternary Goldbach conjecture is now done, right? By using computers and this earlier approach. Okay, so initial applications of circle method are like this. Hardy and Ramanujan used circle method from 1916 to 18 for partition theory. Hardy used for sum of squares. Hardy and Littlewood 1920 to 28 on varying problems. Hardy and Littlewood used for Goldbach conjecture. And of course, other people also, right? The most fundamental observation of circle method is that the function f of x peaks at rational numbers, a by q, suitably bounded denominators. So how to evaluate the integral now? That is the question, right? So that to do that one, this is the first observation, right? So we partition the interval 0 to 1 because 0 to 2 pi I now can think of 0 to 1. Okay, e power 2 pi x I have, right? X is changing from 0 to 1 and I'll full circle I'll get. So there is a bijective from 0 comma 1 to 0 comma 2 pi. So it is sufficient to look at 0 comma 1, right? So this is divided into two parts. This is divided into two parts. So one is called major arc and other is called minor arc, right? So yeah, so I will explain what are major arcs and minor arcs, right? Yeah. So in particular, you look at what is f of 0, right? If you fix n, what is f of 0? So that is sum of pi of n, right? So f of x you see, p less than or equal to e of px. When x is 0, that is sum of primes, right? So when p is equal, f of 1 is also pi of n. 2 also easy to see, right? Except first prime, all others are odd, right? So we'll get minus, so almost equal to, approximately equal to minus pi of. Earlier they are exactly equal. 1 by 3, how do you do? So if you take 1 by 3, f of 1 by 3, you take p equal to 3l plus r, then so e of p by 3 equal to e of r by 3, because at 3l, that is 1, right? Yeah, so we can compute like this. You see that this is actually the Ramanujan sum, r equal to 1 to 2 e of r by 3. It is a Ramanujan sum. R is equal to 1, r is equal to 2, right? And this one. It is also easy when P is equal to R mod 3, number of primes congruent to 1 mod 3 and 2 mod 3 are equal in number. Okay. So that's why we have pi of n by phi of 3. Okay. So by Dirichlet theorem or something later, people proved that their count is almost same. Right. Yeah. So more generally, we can take 1 by q. Right. Then you see that we will get phi of n by phi of q into Euler Mobius function, mu of q. Right. Earlier it is -1, right? So q is 3 mu. So here it is phi of q, mu of q in general, right? Yeah, it can be further extended. Again, you see that this is actually again a Ramanujan sum. Okay, that sum is equal to mu of q. We proved that earlier, right? Okay. So more generally, a comma q also, a by q also will get the same sum. That is a beauty. Okay, right. So this modulus goes to 0 when q tends to infinity. See, phi of q is increasing, right? So it goes to 0. But f contributes more when a by q when for q small denominators. Okay. So that is an interesting point. So we so so to do this one, we need to understand what is f of a by q, right? It peaks at a by q, right? So what is integration 0 to 1 mod f of x dx? Okay. But modulus is difficult to compute because it involves square roots, right? So to avoid that, we will take a square. Usually that is a technique people use, right? Now f of x is a mod f of x square, complex number z into z bar. So we'll get this. So we'll get this quantity. Okay, right. So it is approximately equal to root of pi n average thing. Okay, yeah. So major arcs are exactly these numbers. Around a by q, I will take a small neighborhood. Okay, because the function is continuous. So the neighborhood I will take it will behave similar. So we'll took the major arcs around a by q, where a and q are changing, right? So rest of the part is minor arc. So you convert the integral like two types like this. Okay. So it is overall it is like this. Okay. So minor arcs, major arcs are these and minor arcs. Okay. Over major arcs, generator function f of x very large, but overall length of the arcs is small. Minor arcs, f of x is relatively smaller, but the cumulative length of the arcs is large. Okay. Evaluation technique. Integral over minor arcs requires cutting edge techniques from exponential sums as well as Diophantine approximations. That I'm not going to into details now. Okay. That's why I told gateway of circle method, right? So I'm not going into details. In particular, so we look at the values between 0 to 1, which are very near to this a by q. These q's are bounded by some number, right? Yeah. Okay. So union of all of them is a major arc. Okay. Yeah. So while evaluating it, I will explain you. We'll get some series. Okay. I'm introducing first, then I'm telling you. Usually we'll write later, but I'm putting before. I'll explain you where it comes, this series, singular series, in that evaluation of those major arcs, right? Yeah. So this S of n, okay. So this S of n is equal to summation q equal to 1 to infinity mu of q into C Ramanujan by phi of q cube. It is a ternary Goldbach conjecture. We'll get this, okay. So this R3P of n, that is number of ways of writing n as sum of 3 primes, is approximately equal to this number, right? So that is the idea. So whenever they proved that this value is lies in between C1 and C2, they are positive quantities. That is number one. And also you showed that it is equal to this. R3P of n is this. Because that you able to show that for large n, this n square dominates. So we are going to get a positive quantity. That is the approach. Okay, so how to prove those things? That is very simple. So please note that this S of n is equal to this, okay? Mu of q by Ramanujan into phi of q cube, okay? That please remember that. But instead of Ramanujan, I'm taking this. So this is the Ramanujan, right? I expanded Ramanujan sum. So the Gn of q is equal to mu of q by phi of q cube, but it is up to q only, understand, okay? S of n is up to infinity. So I'm up take up to q only, right? So now this is a multiplicative function of q. Because of that, what happens? It is sufficient to evaluate at the prime powers, right? And also, you know that mu of p power k, if k is greater than or equal to 0, right? So we are going to get this thing only, okay? So S of n is equal to product p 1 plus gn of p, okay? I'm sorry if I'm going a little fast, please stop me. Okay, now our goal is to compute gn of p, this gn of p, right? So that is easy. Mu of p is what? Gn of p. Mu of p is -1, right? It is equal to p minus 1 whole cube. And here what we are going to get, right? It depends upon p divides n or not divides n, right? You know Raman sum, depending upon dividing, not dividing, it changes, right? So that's what we get. Very easy to get this. If p divides n, I'll get 1p minus 1 extra there. That gets, so 1p minus 1 gets cancelled. Minus 1 by p minus 1 whole square. Otherwise, 1 by p minus 1 whole cube we get. So what is the advantage of this? Now S of n is equal to product of these two, right? And this quantity is between 0 to 1 and this quantity is greater than 1, right? So clearly, my S of n is lies in between these two numbers. So these are C1 and C2. Okay, that is the beauty about his proof. Yeah. So big picture is this, okay? So in the ternary, it is working, but binary it is not working. The major reason is this, okay? So main term is very bigger and it contains n square terms, but in a binary conjecture, I'll get n only. And error term is smaller in main terms in the ternary Goldbach conjecture. And the binary Goldbach conjecture, error term is also as big as main term, okay? So for example, in Goldbach conjecture, Mn of this is bigger than the error. Error term means coming from the minor arcs. Okay. So now I'm going to tell you where that series came, right? That S of n came. You take A by Q, right? So where we have the singularities, right? So if we take alpha as A very near to A by Q, we are adding small beta. So f of a by q plus beta, you know that f of x formula, right? Summation p less than or equal to n, right? E power px, e of px. So if you put them and then you simplify, you will get this quantity, right? So it is actually now integral becomes product of these two terms. Here you see that this is actually the my sk of. Here I am directly taking f power k directly, okay? So f power k, sum of n terms, right? So here I will get to that S of k. Oh, sorry, Sk of n. Okay. So that is what I'm saying. Okay. Yeah, these are called singular series. Okay. So, okay, yeah. To have an example, you can pause here and check. Is it every number can be written as sum of three cubes? No, right? There you will get this this series. This sum becomes 0. Okay, if you try this. Okay. Yeah. The main problem is this: p1 plus p2 equal to n. Then P2 I can write n minus P1, right? So that is we are saying that it is approximately equal to n. Whereas in ternary Goldbach conjecture, it is a more freedom is there. That's why it is isomorphic. It is approximately to n square. That's why able to solve. Okay, so so because of all these things, so still I have given some more tables. Somebody is interested. I'm myself also not fully clear. I had to accept that. Yeah, I will go through much better. And you also. So I collected from various places, put at one place so that somebody is interested later can approximate these things, right? Yeah, okay. So these are some of the things related to comparison of the ternary and binary Goldbach conjecture, what is happening. Okay. Yeah, for example, so this graphs may help you later, okay? Because in the cube, so the Raman sums are behaves nicely, but whereas in the binary, binary Goldbach conjecture graph will be little complicated. Okay, so to solve binary Goldbach conjecture, we need a new idea. Okay, why 3GC works, why it remain open, I give some details here. Okay, sorry, I'm not going into details of these things. Now I am going to the third topic little quickly. So this is um, so these are related to some applications of Raman sums. One of the first problem is related to combinatorics. This application is that you take 1, 2, 3, 4, 5, right? Then our goal is to know that what are all subsets of that whose sum is equal to some number, right? For example, how many subsets of this 1, 2, 3, 4, 5 will give you sum equal to 6 or sum equal to 7? You know that total sum can be 15 only, right? You take any subset of 1, 2, 3, 4, 5, sum starts from 0 up to go to 15, right? So this how to get these numbers. It's an example, right? It is an example for 5 only. We can extend it to any n. Very nice problem, right? What are all subsets of up to 1 to n? Subsets whose sum is equal to given number, right? That hope you understand the problem, right? In particular, so how do you go into that? We will take the generating function, right? So when you multiply it, the coefficients will come. So x power 10 is 3, means there are 3 subsets whose sum is equal to 3, right? Hope it is clear to you. Okay. Now, in particular, one question is that what are all some of the quotients is divisible by 2? What? See, some coefficients are whose sum is equal divisible by 2. Some coefficients are not. Sum is not divisible by 2, like that, right? How do you get that? Sum of elements which are divisible by 2. How many subsets of this whose sum is divisible by 2, right? That is simply that collecting the coefficients only, correct? Even coefficients I want to add. What is f of 1 in a polynomial if you substitute? That is sum of the coefficients. F of minus 1 is, you know that. So add, positive, negative will come. If you add them, I'll get to even. But by 2 I do, then I'll get answer, right? I hope you understand. What are 1 and minus 1? They are primitive second roots of unity, right? Similarly, how many subsets of them who is divisible by 5 if you ask? Then this is the sum. Okay, so I gave explanation here, but I will not go into details, but one can pause it and easily understand this. Okay, so we'll get 5 times sum of similar to that what I done earlier. Okay, C0, C5, C10, C15, these are the coefficient divisible by 5, right? There it is divisible by 2, right? So hope you will allocate some time here to understand this part, right? Yeah, so please go through these things. It will be easy to understand. And these are the sets whose sum is equal divisible by 5. 0 divisible by 5, 1 plus 4 divisible by 5, like that. These are all the subsets of 1, 2, 3, 4, 5 whose sum is divisible by 5. Total 8 are there, right? One can compute here. It is a small number. We can write a Python code and you can compute. But large n, we have a direct formula. By nth primitive nth roots of unity, one can derive, or nth roots of unity. Okay, yeah. In the signal processing also, people are using Ramanujan sums. Okay, there is a Ramanujan periodic transforms. Okay, so each is a signals, many signals. So Ramanujan periodic transforms are introduced. Lot of work is going on. I want to inform that. So those who are working in this area can they look. So actually, me and electrical engineering people in our university, we introduced new sums based on the generalization of the Ramanujan sums, complex conjugate pair sums, like that. Okay, so we published several papers by using them. Okay, so not only 4 now, there are many more papers. So for all this credit goes to Ramanujan sums only. Their ideas helped us to get these sums. Okay, and now a little bit of graph theory where I will encountered the Ramanujan sums. It is a recent work. So previous work also there. Right now I'm just showing the previous works. There is a generating graph of a group G, okay, denoted as gamma G. Here vertices are element of the group, and we put there is an edge between two vertices if they generate the group. Okay. So generating graph, but that means that we are going to consider only groups which are at least two generated. Okay. So the cyclic groups are two generated because they are single generated. So two generated also. Abelian groups are of the form Zn cross Zm are two generated. Symmetric groups are two generated. Alternating groups are two generated. Diagonal groups like that. So look at an example. So what is generating graph meaning? You take vertices, let us take cyclic group of order 10, right? So cyclic group, actually not subgroup actually, very mistake. Cyclic group of order 10. So now these are the elements, right? So A is a generator and A power 3 is also generator, A power 7 is a generator, A power 9 is a generator. Okay, then they are already generating. So A is a generator. So with any one it generates, right? A comma 1 is also generator. Those two also automatically generates, right? Similarly, A3, A9 and all, right? But you see that A2 and A5 also generates. A2 is A square is not generator, A5 is not generator, but A2 and A5 also generates. Similarly, A5 and A4, right? So A5 and A6, A5 and A8. So that's why I put a yellow color there, right? It is a generating graph. Okay. Similarly, so 11, okay. So this is a dihedral group of order 8, okay, right. So this is S3 with the 3 letters, right? So on the generating graph of DN. So we published one paper, me and Kavita Samant, generating graphs of finite dihedral groups. It is published in 2023, results in mathematics. So what I want to show that we considered adjacency matrices. We computed adjacency spectrum. Okay. So spectrum meaning that eigenvalues how many times, right? So you see that all eigenvalues are associated with Ramanujan sums, right? And they are integers anyhow. So that's the beauty. The only lambda 1, lambda 2 are not integers. Okay, there is a concept called integral graphs also. And also see that even lambda 1, lambda 2 are connected with Euler phi function. So all of them are connected with number theoretic functions, right? Okay, so Laplacian spectrum also connected with these values, right? Distance spectrum. So there is a graph matrix called distance matrix. The spectrum of the distance matrix is called eigenvalues of that is called distance spectrum. There also we come across the Ramanujan sums, right? Yeah, even eccentricity matrix. So another paper, a dicyclic group, there also we computed. So Ramanujan sums came several places. Okay, yeah. So distance spectrum, eccentricity spectrum, and all that. Okay, yeah. So I explained here what is eccentricity matrix and all. If you need it, then I will read it. Otherwise, I will just skip this part. Okay. So takeaway is that the circle method converts the counting problems into Fourier integral. The integrals fit into major arcs, rational approximations, and minor arcs, oscillatory cancellations. Raman sum arise naturally from the major arc contributions. They encode arithmetic of the problem, local solubility. Method gives asymptotic formula, not exact values, right? For us, it is sufficient. It is positive meaning automatically it is 1, greater than or equal to 1, because they are integers, right? R, S, N of A, they are integers. Positive is sufficient to show. So that's why asymptotic formulas are sufficient. It is one of the most powerful tools in additive number theory. Okay. Yeah. So with this, I will stop. So these are the some of the references related to Ramanujan sums, right? Yeah. So thank you.
Thank you, Satya. We have time for maybe 1 or 2 questions.
Yeah, please. Yes.
Yeah, any questions? Okay, well, maybe a comment. Next time we'll call you once more to explain more about how the sums came up in your research.
Uh,
If that is
yeah.